Okay, so hello and welcome everyone to the seventh week of interactive live sessions for the course on computational fluid dynamics for incompressible flows. So, as you know, this course is being offered by NPTEL. It's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras and I'm the TA for this course. And like every other week, we shall be solving some problems together. Now, this week was a little bit special. So this week we learned what stability analysis and von Neumann stability analysis is, and because so far we have been discussing different schemes, BTCS, FTCS, and so on, and we were commenting on how certain schemes are unconditionally stable, unconditionally unstable, or conditionally stable. These sort of comments we were making, and we were making these out of thin air. We were really not showing where these ideas of stability were coming from. So this stability analysis, and especially von Neumann stability analysis, actually gives us these conditions and criteria which we have to meet. So uh, so that was the main crux of this week. All right, so without any further ado, let's get started with the questions. So here's first question of today's session, which is asking us, and by the way, this is how it works. There will be some questions over here, and we have got four or maybe less or more options given alongside them, which are possible answers to the question. Now, we will read the question carefully, figure out the correct solution, and once we have done that, we can either type it out in the chat box telling that, yeah, I think it's option B, or you can unmute and answer as well. And at any point that you feel that you have some doubt or you would like further clarification, please feel free to just ask. Okay, so no need to hesitate. These are interactive live sessions, so let's keep them as interactive as possible. Anyway, so here's question number one, which says that which of these are ways to analyze the stability of a numerical scheme? Is it option A, the discrete perturbation stability analysis? Option B, the matrix method stability analysis? Option C, the von Neumann stability analysis? Or is it option D, all of the above? So here's question one of today's session, which is asking us that which of these are ways to analyze the stability of a numerical scheme? Is it option A, the discrete perturbation stability analysis? Is it option B, the matrix method stability analysis? Option C, the von Neumann stability analysis? Or is it D, all of the above? So read the question carefully, and once you have figured out the correct solution, you can either type in the chat box or you can unmute and answer as well. Okay, we have a response in favor of option D, that is all of the above. Let's take a look at the solution. It is actually all of the above. So these are all different ways in which we can analyze the stability of a numerical scheme. But as far as the scope of this course is concerned, we really focused on the von Neumann stability analysis because for various reasons. One, that it's robust and as well as simple, and it really gives us insights into uh, where the instability really comes from and uh, which modes are important, those sort of stuff. So von Neumann stability analysis has been the focus of our course, but the other methods are, equally important methods to stabilize, to analyze the stability as well. Yeah, if you have a question, you can ask away. Your voice is
Hello. Yeah. So actually, can you please open the that lecture notes of week six last lecture?
Yeah, thing is, I've lost access to the lecture notes. Let me try once.
Yeah.
Hold on, give me a second. I couldn't log in this morning. I was trying to do that. Lecture notes of
Week six last lecture.
well, if it's not related to this question, let's go through our questions first, then circle back to your questions. Is that okay? So that's related to week six, right? Let's you know this this
Uh,
session first of week seven, and then we can always go back if I can. Okay.
yeah, actually, I had also doubt in week seven also. The
Okay.
first time asking week six.
Yeah, so let's hear your doubts later. Let's go through these questions. And if you have any doubts related to the exact question which you are discussing, then feel free to ask. Otherwise, we will go back to this later. Okay.
Okay, okay.
So I hope this question is clear. So we'll move along to question number two now, which is what is von Neumann stability analysis also known as? Is it option A, Lorentz stability analysis? Is it option B, Fourier stability analysis? Is it option C, linear stability analysis? Or is it option D, all of the above? Okay, so we have a quick response in favor of option B. Let's take a look at the solution. It is option B. Well done. So, do you know why is it called Fourier stability analysis? What is it? So usually when someone asks this, it's not yes or no. What do you think is the reason? We use Fourier series to calculate error. Yeah, basically we express error in its Fourier series. So basically we say that the error as a function of space and time can be broken down into a Fourier series resembling this. So one function of time into another function of space. That's it. So this is a mode of this. So yeah, and goes from 0 to n or infinity basically, not just n. So this is so we do similar to this, and then we try to analyze what the growth rates are. So if the growth rate is positive, that means that the error is blowing up. It's increasing with time. If it's negative, that means the errors are dying down. Yeah. So good. So I hope things are clear about this. We will move along. We'll move on to question number three, which is asking us what are the minimum and maximum wavelengths of errors appearing in von Neumann stability analysis with n grid points and delta x as the uniform grid spacing. So basically, if our whole domain is like this, let's say it goes from x equal to 0 to L, and we break this down into n divisions such that delta x is equal to L by n. Then what is the minimum and maximum wavelength of error that can appear in this? So there are four options given here, delta x and n delta x, and the template over here is that the first one is the minimum and the next one is the maximum. So option A is delta x and n delta x. Option B is pi by delta x and pi by n delta x. Option C is delta x by pi and n delta x by pi. And option D is 2 delta x and n delta x. Okay, so we have a response in favor of option C, that is delta x by pi and n delta x by pi. Okay, so let's take a look at the solution. It's actually option D, 2 delta x and n delta x. So the reason is pretty simple. So if this is my domain, so the largest wavelength is what resembles this. So basically something like this. So here the wavelength is the whole length, right? So the whole length L is basically n into delta x. This is the maximum wavelength possible. And the smallest wavelength is just two spacings. So basically, if we start from here, sorry, if we start from here and go like this, so each spacing is delta x, and this wavelength therefore will be 2 delta x. That's the minimum wavelength. So the minimum is 2 delta x, this one, and the maximum is n delta x, this one. Yes.
Actually, why I just want to stop you because I'm not able to start the week because of these basic questions. So I just request that if you can first address the doubts because I have not not able to take the lecture, so even I cannot answer these questions much.
Not able to take the lectures meeting?
Because I have some basic doubts in this what waves and all that you start. So I got stuck over at that point and not able to continue with the lectures. So I just want to request that if you can first go by doubts, so
Okay,
that will
let
be.
me check if I. So you need the lecture notes for that, right?
Yeah. Otherwise, it will be difficult to ask questions.
Okay, let me check for that. So I don't have access to the new course. Let me see if there's an old course that I can get access to. Week 6, right?
Yeah, week six, lecture two.
Yeah. You can't see my screen as of now, right?
Yeah.
Can you see it now?
Yeah. Now I can see.
Okay, so week 6, which lecture? One or two?
Two. In the last uh, this no, this Mac Cormac method.
McCormack's.
Just previous select.
Implicit drivers can be McCormack.
Yeah.
Okay.
Yeah. Now here I don't understand what exactly happening because till now Not this one. Maybe previous slide. Previous to previous.
Okay. This one?
No, no, no. The previous.
This one?
Yeah, this one.
Hmm.
Yeah, from the very basics. So basically, I don't understand this, the philosophy behind this. Generally, what we are doing, that we are either taking forward time step or backward time step, or we are central spacing. Those things we are using.
Yeah.
Here we have used some basic, some
Multi-step.
yeah, multi-step, but some predicted, or what that step is called as.
Predictor character. Yeah.
Yeah.
Hmm.
So where is that step? In what time step we are having this time?
Hmm.
Because once we have calculated this star, the predicted step,
Hmm.
then we have used n plus one, n plus half, like whole philosophy. I didn't get it. So
Yeah.
can you explain it from the very beginning, that
Yeah.
how
Yeah.
this?
So the main thing is my time step is still delta t. It's not anything different. Just the thing
Hmm.
is, while jumping from
And present time is previous time step is n, present is n plus one, like this ways.
so see once again present and past. Don't think in that way. So
Not
n is known, n plus one is unknown. You're while
okay, okay.
moving, you're just doing that. Yeah.
Hmm.
So yeah. So basically, we are going delta t itself, not more than that, not less than that. But we are not going in one step like we do in either backward time or forward time, right? So those methods are just one step. So here it's a multi-step method, meaning that I am still trying to predict the same thing, what is at n plus 1, but I'm solving two equations for it. I'm breaking it down into two steps. And those two steps, as proposed in this method, is that, the first step, that is forward difference. So basically, I'm using all the known values at n, find out what the values could be at n plus 1. I'm calling that, the, uh, what is it called? Some intermediate, or some predicted value. Okay, so this is exactly similar to what you would do in forward difference. So then in the next step, what is done is that uh, it assumes a half step going from n plus half to n plus 1 and using a backward difference for it. And the n plus half, since we have not calculated n plus half, right? We have only we
Yeah, sorry,
know.
sorry. Just a minute. I'm really sorry.
Yeah.
I missed it.
So
Uh,
first you do a standard
Actually,
forward difference and get a guess value. That is that star value. Okay.
at what level this is?
That is n plus 1.
N plus one. Star is n plus one
Star
level
is
only.
n plus 1. Yeah. But you don't
Okay.
stop there. So that's like one guess value and you try to correct it, improve it. So how does that
Okay.
improvement happen? That improvement happens in this way, that you, you consider now another step going from n plus half to n. And you know what the value at n is, and you have a guess value at n plus 1, which is the star thing. So
Hmm.
now your guess for n plus half would be the average between these two. So this is this step over here. So n plus half, you just calculate as the average between n and the guess value at n plus 1, which is the star value. And over here you use a backward difference. So now you get the benefits of backward difference, which is it becomes unconditionally stable.
Just 2 minutes.
Yeah,
Previous slide, please, please. Now I'm understanding. So let me correct me if I am wrong.
yeah,
That our intention is to calculate the value at n plus 1.
yeah.
We go by, so first,
Hmm,
since we are using forward spacing,
hmm,
so first this star is actually some guess values
hmm,
at n plus 1 level only.
yeah,
Then in second we have used backward spacing.
hmm,
So but in backward space we go not go to n level, we go to n by n plus 2 level up to
Yeah, n plus half. Mm.
n plus half level. But our intention is to calculate this phi I n plus 1,
Yeah,
right?
yeah.
So this is in time. So if in space we have to be at nth level.
No, backward difference when you're doing the in the second step, you're going to n plus half itself.
Yeah, n plus half, but
No,
currently
no,
we are
sorry,
at.
sorry. Let me correct. So not n plus half. In backward difference, what you do, your spatial differencing is also at n plus 1 itself. So since we do not know what the values at n plus 1 is, we use those guess values, those star values which we had calculated. So in the right hand
Yeah.
side, you have those star values, n plus n plus 1.
Okay, but okay, but what we have at this I n plus half,
Hmm.
we will get by average of this.
Yeah.
Okay, but from where we get this phi I minus one, because we have calculated phi I star,
No,
but
no,
phi I minus one
we
star we have not
calculate
calculated.
for all i's.
Okay,
Yeah,
okay,
I is
so
just
okay,
representative.
so from first equation we have calculated all i's, all
Yeah,
nodes
yeah,
basically.
yeah.
And now I am using backward spacing,
Hmm.
keeping myself at n plus 2 level and moving towards nth level, n plus 1th level,
Yeah,
right?
yeah.
So, so at time step, I'm taking at n plus 1, which is n plus 1, which is unknown. But for space, I use those
Known,
guess values.
known values. Yeah. So it's sort of a mix. Like you don't do a pure backward difference here because in a pure backward difference, these values at the right hand side would also be unknown values at n plus 1. But since we have a guess for what it could be at n plus 1, we take those guess values, the star
No, no.
ones.
Can you what? Can you repeat this?
So if this second step was a pure backward difference, then on the right hand side, the space differencing, there also it should have been phi I n plus 1 minus phi I minus 1 n plus 1, right?
If it is pure time,
Pure
then we
backward
have
difference, yeah.
pure means spatial coordinate we don't have. We have only time coordinate.
Hmm.
Then
Uh,
no, I don't understand what you
Yeah,
are saying.
so if it was a pure backward differencing scheme, then this second equation. So on the right
Hmm.
hand side, sorry,
Ah,
in
yeah, yeah, yeah,
previous,
yeah, yeah. Okay, now I get it. What you're saying, trying to say. Okay, okay. Now in this method, we have used this special thing that guess values we have used for space,
hmm,
and the previous this I n plus one we go and take this at average. Is just I find it like just randomly we are doing all this.
no, these things
Yeah.
appear random because the groundwork behind this is not being shown. But for that, you have to find out the research which McCormack had done. Maybe there is some paper which contains the details and the philosophy behind how that person came up with this. But we just study what it is
Hmm.
and what are the advantages, disadvantages.
Okay. So basic. Okay. So can yeah move ahead. You can move. Yeah.
So
So
which
next.
which lecture next?
No, no. Next slide.
Oh,
Yes,
next slide.
because this. Yeah. So here we have this. Just lambda. This is just calculations. Okay.
Yeah,
Okay. Yeah.
same
Yeah.
same equations, just simplified down. So in
Okay.
the first step, you
Predictor and.
calculate the phi I star for all I. Then you go to the
Hmm.
corrected step and then find out phi n plus 1 for all I.
Okay. And okay. Yeah. Okay. Now the same thing is like for seventh week lecture one.
So
was first is. Yeah, please go move from. Yeah, like here, just stop. Uh, First of all, I don't understand the again the here the same basic philosophy behind how we are calculating the errors and how Fourier series comes to play to
Mm-hmm.
evaluate the error.
Mm-hmm. So do you know
And
what a Fourier series normally does? Like forget error and everything. What a Fourier series
mhm,
is?
uh, yeah, I don't remember the series,
Okay,
but
so
I know that there's a different yeah, if you can please
yeah, so
take a.
basically, so we can go into more detail if you want, but the basic thing about Fourier series is that let's say any function I give you or any time series if I give you that there's a series of numbers and you know at what time these happen. So basically, I tell you that delta t is
You can
1 second,
you
and
sorry, can you take some blank that you can write.
for that I need to switch something. Okay,
Yeah, if you can explain it because it's a long doubt, long like from like how Fourier series comes to play and what exactly it does.
can you see my screen?
Yeah, yeah, yeah.
Perfect. Yeah. So what Fourier series basically does is that let's say if I have any function of x and time, okay,
Okay.
they is broken up into a series of sine waves. So let's call them a1 sine some lambda 1, not lambda 1, k1 x plus a2. There's a a0 as well, which is a constant plus and a2 of time plus sine of could be sine cos or both, doesn't matter,
Mm.
and this is a infinite series like this. So the main use of this is, let's say, forget space for a moment. Let's say if this was um, well, no, this was only time, let's say. So let's say I had only time like this. So in that case, these would be like this. So a0 would be a constant, a1 sine k1 t plus a2 sine k2, like this. So this is a Fourier series in time. So what this basically does is it helps us change the table that we are looking for. So let's say the original description was like this. We had
Now, if yeah, 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 please
we
quote.
had time
Then
in
I.
the x-axis and our f was something like this. Now
Mm.
breaking this up into this time series, now this whole game changes. So basically now I can say k is some um, x-axis and I have amplitude a on the y-axis and a is a function of k obviously because you can see that the a's and the k's are related to each other.
What is K?
K is the wave number, so it's basically like 2 pi by omega, where omega is the frequency, or 2 pi by f, or no, we are already using f. Omega as well. So it's like
Can you?
frequency of sine wave.
Mm,
Sine
what?
waves have a frequency associated with it, right? So how fast is it going?
Okay. No, can we go by this like time? If we are introducing time, then it is difficult.
Mhm.
First, can I say it like you? What we do in Taylor series is like we express any function in like in the polynomial form, right?
Not
That is Taylor series.
polynomial. Those are as a sum of derivatives in Taylor series.
Yeah, some of the derivative. Okay, but and here we do the same thing, but as a function of as a sinusoidal functions,
Yeah,
right?
they're not exactly same, but yeah, they're similar. Like they're both expressing something as a infinite series, as a sum of an infinite series.
Okay, so like how this frequency come into play for this thing?
So k is basically a representation of that frequency, nothing else.
Yeah, that representation of frequency, but how did what is the use of frequency here?
Yeah. So the use is this. So now you know like which sine wave is most dominant. So you can see this for a certain k there is a high amplitude. So it's like that's the most dominant frequency in the original signal. And to do a so these are in continuous series. So uh, there is a discrete version of this as well. So let's say you have discrete time series like this where it goes bam 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 bam. Then you get discrete uh, frequencies as well. Then you can know that okay, this frequency is dominant, this frequency not
Oh,
dominant, this frequency
no,
is
no,
more
just a
dominant,
minute.
like that.
Actually, the thing is, we are moving too fast. Sorry.
Okay. So
Uh,
see, Fourier
let's
series
see.
is not a part of
Let
this course, so it will be better if you go back and read up on this.
Yeah, yeah. Just a little thing I just want to know that the first graph you have shown F versus T,
Hmm.
right?
Yeah.
Now, can I say it that I make a curve of F and T
Hmm.
and A naught alone? Then again, I then second curve of A1 sine
Hmm.
K1 T.
Hmm.
Then third, if I add all those curves, I will get this
F. Exactly. So
exactly,
so
right?
exactly. So it decomposes it into multiple sine waves.
Okay. Now, to now this now if I am making this second portion curve, is just I am asking like maybe it is not a part of course if you are
No, no,
uh,
you asked already.
okay. So if I am in this a naught, I understand
Hmm.
simply. Can you make one curve like f versus t and simple a naught?
No, A naught is just one value, right? A1, A0,
Yeah, yeah, so
A1,
it is a constant over the
those
time.
are constants, yeah. So
So
this whole thing can be, made into a sine curve. So basically, let's say,
no, no, like f versus t and make a constant line a naught at f.
oh, okay.
F
So
is equals to 8.
I can draw this here itself. So it's like a curve. This is,
Yeah.
yeah.
Now the second A1 sine K1T. How I made this? Can you make second graph? A1 sine.
A1 sine K1T. That should be a perfect sinusoid.
Yeah, but okay. But A1, so we have to start. Okay, we have to start from some above point at y-axis or at
No,
zero only.
no.
At
The,
zero.
yeah, the mean will be at 0. So then
The mean.
some into sine K2T.
Hmm.
Yeah, something like that.
Okay. Now, when
Now,
we
now
simply
if
we
you
made
add these
multi
things up, yeah, that will give you back the original.
original, yeah, that's what I am step by step understanding. So now I focus on one curve a1 sine k a1 sine k1t. Okay,
Hmm.
now here a1 is the amplitude,
Yeah,
okay, and t obviously the time at which
the x-axis.
yeah, and k1 is the frequency.
K1,
So
K1 represents the frequency. So 2 pi by omega is actually K. So basically, K is the, so your frequency is this, right? Okay, so
um,
here your time period
frequency we
is,
cannot express here. It just means at one point how many waves are passing. That's what we
yeah. So
say in one second.
basically, no, I'm trying to relate it to this curve. So basically, your uh, time period is this.
Hmm.
So your
The wavelength.
so your frequency would be this pi by tau, right?
Hmm.
And your k over here is nothing but pi omega. K is 2 pi omega. So that should be omega is now 2. Oh no, sorry. 2 pi of the sine, so it would be this way, right? Pi of omega. Okay, sorry. So this 2 pi can be there. The omega is 1 by time period.
Hmm.
K is 2 pi omega. So basically 2 pi by time space.
Okay. Hmm. So, but so somewhere it gives 2 pi by tau omega and omega frequency time period. So, but basically tau is what this wavelength.
The time period over here. See, wavelength and time period are similar. Now, wavelength is in space and time period is in time. But yeah, the concepts are the same.
Okay, so but wave number can give me an idea of how much is the wavelength or time period, right?
Exactly.
Yeah,
It's directly connected.
it's directly connected. Okay, so now I get some extent. Now, what you are explaining about A versus K in this?
Yeah, A
Uh,
versus K is basically what is my A for a given wave number K.
okay,
So that
and
contains
in
all the information of what F versus time is. Right?
okay, so A versus K will give me that relation between amplitudes at a particular wave number.
Exactly. So if you now
Ex-
take sine waves of wave number K and multiply them with the amplitude A, that given A, then you will get back
hmm.
F. So basically, that's the same information conveyed in a different language.
Okay. Up to this extent, I understand.
Yes.
So this is about Fourier series. Now, how we are using this thing in while our
Yeah.
stability analysis error
Yeah.
calculation.
So basically, uh, in our case, we are expressing our error in a similar fashion like this. So the only difference between this one and this one is that this one was a function of time alone, but error is a function, you can imagine, of the space as well as time. So there, what we do is these amplitudes, they become a function of time, and the sine waves, they are sine waves in space, and we consider them that those waves can either grow or decay with time. Okay.
Uh, no, like
So
I'm sorry, it's difficult to get built up, but basically we have this. Okay, yeah, this is error, and this error is a function of space and time, right?
yeah, so basically it is something like this. So this is x now in the x-axis. So let's say this is first one. So this is k1 comma t into sine k1
This is first
k1x
wave.
k1x. Sorry, this is the first wave. So k1 tells me what this wavelength will be,
Okay.
and first part, the k1t, tells me whether this will grow in time or decay in time. So if that's positive, this particular mode, this will become something like this.
Okay, so here amplitude is also function of time.
Amplitude is function of time, and the sine wave is a function of space.
Okay, and this is about only the first part.
This is
Then there
only
is
one. Yeah. So now here's the fun part. So the thing is, von Neumann stability analysis can only be applied to linear systems, right? So that was told in the lecture. But anyway, so if it's linear, then I can consider only one mode, and then all the other modes will also behave in the same way. So what I'm telling is, so in this case, so I can consider, let's say, only this second mode and see what A2 with time is, and that will tell me exactly how A1 with time or A3 with time or AN with time will behave.
Okay.
Like the growth with respect to time would be the same since it's a linear system.
Uh, yeah, but hello.
Yeah.
Yeah, actually, your camera is still. Okay.
So I'm busy sharing too many things with you guys.
Okay. So, but how this conclusion came? Like, if it is
What?
this that if it is a linear system, then all this will happen like behave in the same way.
Yeah, so if you look at the, the um, so let's open the lecture notes.
Okay, so till now, so I just what you said. Just tell me if it is wrong. Hello.
Yeah.
So basically, we have error, which is obviously random in nature.
Hmm.
It is function of space and time,
Yeah.
x and t,
Hmm.
and we express it as a Fourier series,
Hmm.
which is a summation of multiple waves.
Hmm.
Now we only focus on one wave because it is
Yeah.
linear in time.
Yeah.
Okay. Till up to this step, very difficult with that quite difficulty, I understand.
Okay.
Okay. Now the question is
Why?
like how from where
Yeah.
this question came.
Exactly.
There, yeah.
Yeah. So let's take a look at this thing. So the first example that Sir showed. So this is my unsteady diffusion equation, and
I'm not able to see your screen. It's saying you lost your network.
is my screen not visible?
No.
Can you see?
So it says your connection. You lost your network connection. Trying to reconnect.
Okay. Let me know when you've connected.
Okay. Hello.
Yeah. Can you see the screen now?
I think no. Actually, I should reconnect again.
Okay.
Just
Okay.
please 2 minute hold.
Sure.
Uh,
Hello, can you see the screen now?
Yeah, yeah, yes. I sorry. Okay, so yeah, from where this philosophy, this
Yeah,
thing come?
yeah. So let's take a look at this example. The unsteady
Hmm,
diffusion equation. Rho phi rho v
hmm,
equal to gamma rho t rho x squared.
hmm,
Now, here this idea comes in that uh, the numerical solution of the finite difference equation is nothing but the exact solution of the same infinite difference equation plus the
hmm,
error we suspect. So n equal to epsilon plus d. So
hmm,
since once again, since it's a linear equation, I can split up this n into epsilon plus d, and there will be two different equations of the same equation with d will be the same equation with epsilon. This part is
hmm,
clear, right?
hmm.
So now these errors, these are now functions of space and time. So now if you had replaced these epsilons with that series, that Fourier series of all the different amplitudes, split those into all. So let's say if you took n different frequencies
Hmm.
or wavelengths, sorry, not frequency, wavelengths, because waves are in space and they grow with time. If you take n different fractions with epsilons corresponding to each wavelength, and they will be the same equation.
Okay, what? What?
Okay, so I have to write this. Yeah,
And just before changing, I have a doubt in this also. Like
yeah,
while we are, hello,
yeah.
yeah. So in the previous slide,
Hmm,
can you previous slide? Yeah, here I understand. First of all, the exact solution of PD is far away.
hmm,
That is a different thing.
hmm,
We are focusing. We have an exact solution of FD,
hmm,
and we have a numerical solution of FD. We are truncating some terms,
hmm.
right? That
Yes,
is the difference.
yeah,
Okay, now definitely I understand this. We can write n is equals to epsilon plus t, and it was told that it will, because this numerical solution will obviously satisfy the equation, so we put it here.
yeah.
This much I understand,
Hmm,
but at the same time, d, which is told to be
hmm,
the exact solution,
yeah,
that also will satisfy
hmm,
this thing.
yeah,
How it makes the difference means numerical solution will also satisfy the equation, and this will also satisfy this.
yeah. So what's the definition of a solution?
Yeah, that's okay, but those both solutions are different. There's an error in between.
Yeah, but one equation can have multiple solutions, right? X squared plus 2x plus 1 equal to 0. How many solutions does that have?
That has two, but where we are taking here only one solution, that is d, which is our exact, this from the same solution we have truncated some terms. So it is a derivative. N is the some derivative solution of d, and we are truncating the epsilon terms,
So
right?
basically, the same equation is satisfied by three different things. By n, which is the
Hmm.
numerical solution, by
Hmm.
d, the exact solution, as well as the error, epsilon.
No error. Oh, error I understand. If I can write second equation, then I can subtract and can say that
Yeah,
okay, so error is also
but this
satisfying.
also satisfies that original equation, right? This is also the epsilon is also a solution to the original equation, right? This rho phi
No,
rho t equal to gamma
epsilon is
rho.
the error.
Yeah, so no, it is a error, but given that that phi equal to epsilon is also a solution to this equation.
No, let me put in a different way the same question.
Hmm.
We got d if we can infinite terms if we can calculate in Taylor series. Okay,
What? Sorry.
the d, which is the exact solution of finite difference equation,
Hmm.
we can have it if we can calculate all the infinite terms, right?
All the what terms?
Infinite terms in the Taylor series that we can calculate. That is the exact solution of finite difference
No, no,
equation.
no, no. The exact solution of FD is if there was no round of error. If you had a computer which could go up to infinite number of digits, then the solution that you would have got using that computer is D. Now, since real
Oh,
computers have a finite accuracy, we truncate at, let's say, what, 16 terms or 64 terms,
no,
depending on
no, no.
the
Wait. I
notation.
am saying truncating up to second order or third order.
No, no,
That
no,
is
no, no,
truncation.
no, no. That truncation is not coming here. That truncation is the difference between A and D.
Okay. If we can calculate the infinite term, then we get exact solution.
Yeah,
Okay.
not
That we
infinite terms,
truncate.
infinite digits.
Okay. And then we first truncate, so we get D.
Yeah,
In truncate, we round off, so we get N.
yeah,
And this round off, we say it as a numerical solution.
exactly.
Okay, so definitely then both can be put in the equation. Okay, actually, what I am confused is like in D maybe there's an infinite terms and there are limited second order up to third order terms.
So FDE, right, the finite difference equation, this equation, the I n plus 1 minus T I n by delta T, this equation.
Hmm.
That's the
Yeah.
FDE, and that FDE has, it has a hypothetical exact solution. We can never get that, and
Hmm.
there is a numerical solution n which we do get. The difference between the two, which is epsilon.
Actually, I got confused because FD itself is a numerical thing. So I got
Yeah,
numerical.
it's a discrete thing. Exactly.
Yeah, so it is. So I that's what I say that numerical FD is also a numerical. Where is the exact thing about it? That's why I got confused in the terminology.
Yeah. So n is the only number that d and epsilon are unknown stuff.
Yeah, but it's better to use a round off solution of FD.
Yeah, that's what.
Then,
Yeah, that's implicit when we are defining a, d, and n.
yeah, okay. Yeah, you can. Now I understand this stuff
Okay.
that we can put this equation and epsilon also. Like if we subtract, then epsilon also. Yeah, now you can move
Now,
ahead.
so coming back to your earlier question, that why can only one epsilon tell me everything? So there are, epsilon is a sum of multiple sine waves, right? Why should
Yeah.
I consider only one sine wave? So
Hmm.
coming to this equation now, the epsilon I n plus 1 minus epsilon I n plus 1. This one, you can see my cursor, right?
Yeah.
Yeah. So in this equation, if you replace each epsilon equal to sum of those infinite sine waves, and then you split up this equation into the same number of equations. So uh, for each sine wave, one equation you will get. So those will also be same equations, right? You get my point, or should I type it out or write it?
If you can write it
Yeah,
is better.
that will be better. So stop sharing here. So I need some space. My equation was this: epsilon I plus 1 minus epsilon I n delta t equals gamma. Then whatever. Epsilon I plus 1 minus epsilon I plus epsilon I minus 1 all of which by n plus 1. Okay, this is my equation. Now each epsilon, as I told you earlier, is equal to uh, a sum of multiple sine waves.
Yeah.
Let's call it An of sine of Km, Km of x. Okay. So these epsilons, all of them, I split them into a series like this. Let's use two only. Okay. So
Hmm.
sine x. So this will now be epsilon y n plus 1 other. This will be a n a1. Let me write this. So this is a1 sine k1 plus a2 sine k2. I'm writing b a1 sine k1 plus sine this, right? So this one now, this one will be a1 that plus delta t sine x a1 x plus a2 plus delta t. This will be a long equation, but anyway, this is just this term, but we have to subtract a1 and then plus a2 towards I'm just doing the LHS. Okay, so this whole thing
Yeah.
divided by delta t is the LHS, this one,
Mm. Yeah.
and I'll have a similar right hand side as well. Now if I
Right.
pick, let's take only sine k plus 1 common, sine k1 x common, then I will have this equation a1 t plus delta t minus a1 t divided by delta t. This is the LHS, and I take sine k2x common, then I have a2 plus delta t minus divided by delta t. And similar things, like if you group things into angles
Yeah.
according to the same amplitude, then you'll get the same form of equations.
It is kind of same sinusoidal wave.
Same sinusoidal waves. So you can consider just one. You don't need to consider all. That's the main thing. And this happened because everything was linear. Imagine now if there was a product, let's say some epsilon n plus 1 into epsilon n, then this
Mm-hmm.
won't be true, right? You can't split it this way.
Yeah.
This is the reason why if it is linear, then consider only one equation is the same as considering all of them.
Oh, nice, nice. Now, can you move back to the presentation?
This is the lectures.
Yeah, yeah, yeah. Lecture.
Manual. Keyword.
Sorry, I'm really sorry.
Okay. So did I stop sharing?
Yeah.
Mhm. Check. Is it visible?
Yeah, yeah, yeah.
Hmm.
Now, can you move on previous slides?
Previous slide. This one.
No, further previous. From here, I understand. This also I understand. Yeah, here above. Yeah, from here now, uh, the same actually we can also write in exponential form.
Yeah,
Same.
that's the what is it called? There's a name for this, right? Oh no, I forgot. Forgetting school stuff. So epsilon to the power minus I kx is basically cos kx plus I sine kx, right?
Yeah. So basically, here what we have done with the same sinusoidal Fourier series, we have written in this form.
Yeah.
But this extra, this cos and all those terms comes, but obviously it comes with iota. So
Hmm.
I mean to say that both are same
Both are same.
exactly.
Yeah, three things are same. Only cos sum of cosines, sum of sines, as well as sum of these epsilon I kx. They are all the same. They behave in the same way.
Okay, so just we have written it in a different form,
Yeah,
and it is the
this
same.
is more general. I mean, this considers both cos and sine.
Okay, now can second slide, next slide. Yeah, here this thing. Now, can you enlarge it?
This
Enlarge.
image.
Yeah, yeah. Here now this big wave and this small wave. What does it mean that there are different components of sine? So sinusoidal wave. So the smallest and the largest wave. That is what we are looking for.
Exactly. So in a continuous, so when we did f of t equal to sum of the sines, so
Hmm.
there k was a continuous function and the number of terms in that series was infinite. Now that is in a continuous sense. In a discrete sense, I cannot really get all the wavelengths. I can only get discrete wavelengths. And even within that, there is a maximum one which goes from, minus L to L in this case.
Yeah, how k can be continuous? Like,
K
acha,
can be
because it
anything.
is infinite
Frequency
series.
can be anything, right? Frequency is a real number.
Okay, and while we are like we write this Fourier series, we actually like
To consider
very
all
with
the possible options.
acha, okay. Consider all the possible options.
Yeah.
But in actual, we have only these possible waves.
Yeah. So basically, I made a mistake. So when it's a continuous thing, then we do not really express it as a sum. We express it as an integration.
Yeah, obviously. Okay. Yeah, see, it is same thing. Integration of like
Yeah, no,
some.
because it's continuous, we have to integrate it.
How does it make difference that I don't understand? Because
No, no, see, if it's discrete, that K1, K2, K3, then doing a sum makes sense.
it's
But
yeah.
if K is a real number, then you have to consider sum of all the Ks, right? So
Yeah, then it is
then
in
it becomes an
integration.
integration.
But here we are taking summation, but still we have this limitation that we can have a maximum or minimum,
Yeah.
right? But from where did these things come? Like this delta x we have taken.
Hmm.
What is this delta x like?
What is this
This
delta?
is
So you watched, 7 weeks of lectures on CFD,
no,
then
no,
you
no.
are saying that.
Just a minute. Let me explain. This I mean to say this. Uh, when I am writing this from minus L to L, it is the actual domain where we have calculated the solution,
Hmm.
and at each node, this is the error.
There's the error, yeah.
Okay, so this is okay now. I understand. So means I think that this x is different and that domain over different
No,
is
no,
different.
same thing. Spatial discretization is the same.
Spatial discretization. So in that we have this error. Okay, now I understand. And when I make only one wave, it doesn't mean this is the error. This is only one component of error.
Exactly. Correct.
And the smallest possible wave is this and the largest is this. Okay, but if I had this one component which is the smallest one,
Hmm.
it do not cover the whole domain from minus L to L.
No, no, it's just showing one wave. If you continue that, then it covers the whole domain.
Oh, okay. Yeah,
This is
now
just to
some
show.
huh?
This is just to show that this is the wavelength. Now, if you continue it towards left, towards right, you get the whole. You'll cover the whole domain.
Okay, okay. Can you minimize, shorten this so that I can see the content nearby? Yeah. Now here the error is superposition. That is okay. And now we have defined this delta k, the wave number and all those things. Okay, yeah, that's okay. Can you
No
go
worries.
to the next? Yeah, next slide. Yeah, here there are, yeah, this red line.
Hmm.
Since the error tend to grow or decay exponentially with time, it is reasonable that amplitude varies exponentially with time. First of all, this we have written road term since finite difference linear. Acha, okay, the blue term you have already explained that if like the finite difference
Linear.
are is linear, means the behavior is linear if the equation is linear. But what about this exponential? We have taken this as sinusoidal. So why we are
It's
saying
sinusoidal in space, but in time it's exponential. So this first line, that since the error tends to grow or decay exponentially with time, this has been experimentally observed. Like if you compute the growth of error in an unstable scheme, you will see that it follows exponential growth
exponential
with time.
or decay if it is a stable scheme?
That decay is also exponential.
Okay, so that's why we have taken amplitude. So we only, but we put this condition only on amplitude, varying it
No,
as
yeah,
exponentially. But
a m of t. We say that this can be written as epsilon power a t over
hmm.
here. So this one.
No, no, but why don't we put this thing, this condition on this sinusoidal thing, like a sine term, the spatial varying?
Yeah, because that's not exponential. That's just I have an error and I'm splitting that Fourier series.
Okay. But at particular node, it's necessary. It is not necessary that at the end point or somewhere it is zero because it is sinusoidal. So it will start from zero, end from zero
Yeah,
most of the
but
time.
cosines
But
do not do that, right? So that's why this you know e power ikx becomes important because that considers both cos and sine. So you are right. So sine would start and end at zero, but cos doesn't have to do that, right?
okay, so but that Fourier series, what we have discussed there, only we have taken sine term.
Yeah, but that also can consider it. So there was a a0 which I had considered, right? A0 takes care of it. So A0 plus all the other sine waves, they can give you any value.
Okay, okay. Now here, okay, so I understand to some extent. Actually, this is the problem because there's two things. One thing itself, it is difficult maybe to understand, but at the same time, I have read this before,
Mhm.
different source,
Mhm.
and the introduction is very different from this,
Yeah,
and I have
each
not continued.
each
And
teacher will teach the same thing in a different way, right? So those are
yeah, and the second thing, it is a very like very depth in very depth,
that's true.
so
Yeah,
it
so
confused.
Professor Dalal is like that. So if you look at his other courses, he has a course on convective heat transfer as well. So there also he goes down to the full detailed applications and things like that. And this course is, this is CFD theory basically. This doesn't teach you how to do CFD as you do in industry or something.
Yeah, yeah. So
You're
okay,
basically
so
learning the fundamentals and theory of CFD.
yeah, so we seek so what we have done here, this thing that epsilon we have assumed here, we seek solution of form.
Hmm.
Now this thing what we have, what is written below this red line, this I don't understand. Can you step by step explain
From
it?
the Z power n.
Yeah, from the epsilon x, this is the normal we have assumed. Now we seek solution of the form means.
Hmm. So this again goes back here that the error grows or decays exponentially with time, right? So n is the time step,
Hmm.
right? So if it's exponential, then each time step it will get multiplied by itself, right?
Yeah.
That's what exponential means. So basically, at the nth time step, the amplitude will be something power n. That something we're calling z.
Okay. And then we assume this z
Hmm.
to be e a raised to
Yeah,
a
e
delta t.
power a into delta.
What is this a? Is this relation with amplitudes?
Yeah, so that's the growth rate of that amplitude. So if a is positive, that means that it will grow in time, and if a is negative, that means it will decay in time. because it gets multiplied to itself every time step.
Okay, so but AMT we have written as now the actual error is AE iota K MX.
Hmm.
Now this AM again we are writing it as ZN.
Z
Now
power
this
n.
that now
Z
this
power
Z.
n, see, Z power n is just an intermediate step. We are ultimately coming down to this e power
Yeah,
n
yeah. So basically we are expressing this amplitude term also in exponential term
in
in
exponential.
exponential.
Yes.
Okay, because we because we make
No, that
we are able to make this conclusion that it is also going to change exponentially.
exactly.
Okay, now okay, up to the next A maybe complex also it was
Yeah.
told.
Yeah.
So
So it
how A
can,
can be?
so A being, so if A is real, if the real part of A is positive or negative, that you can understand, right? Whether it can grow or decay.
Okay.
But if there's a complex part, then it will oscillate as well while growing or decaying.
But the spatial thing we have already considered.
Forget space now. Space is fixed. For one
Hmm.
spatial mode only, you're worried about what happens to the amplitude. So
Okay.
that amplitude can, go up exponentially, it can come down exponentially, and on top of that, it can oscillate as well. That oscillation part is can be taken care of by this uh, imaginary part of small a.
Okay. So we move from time t1 to t2.
Hmm,
So it may grow,
hmm,
it may decay,
hmm.
and it may oscillate. What does this oscillate means?
We'll have to draw for that. So, do you want anything else from these slides? Let's go
Just a
through that,
minute.
then I can
Yeah, yeah,
switch back to the presentation.
yeah,
So
yeah.
let's go through the slides. Let's see if you have anything else. So here we're defining
Yeah,
the
now up to this level, okay, clear. It is clear. Now you can go to that. Uh,
okay.
Hello.
Yeah, absolutely.
Yeah.
So A, what can A do with time?
Yeah.
It can decay exponentially,
Yeah.
it can grow exponentially,
Yeah.
and it can oscillate while doing both. So if A is positive, this is what happens. So the real part of A is positive, then this is what happens. This is what happens if real part of A is negative, and these oscillations happen. Frequency of those oscillations again would depend on the imaginary part of
Okay. And so if let's say if I am at T1
it.
at some point,
Hmm, hmm.
then it would be a summation of this oscillation part plus real part.
Yeah,
That was okay. So it is taken care of all type of possibility that could happen.
exactly.
Yeah, yeah, yeah. Okay, okay.
So
Thank you very much. You have taken so much efforts and time and patience, obviously, to
that's
hear
okay.
all
It's
my
my
questions.
job. Okay, so let's come back to the questions now. Come back to
Thank
my
you very much.
questions.
Yeah, yeah. Now I can actually I have not moved forward.
Hmm.
Only the first lecture I have taken, and then I got confused over there because even in the sixth week last lecture I got confused, and then here also I confused. So I am not able to move forward. I am waiting for you to come and explain these things.
That's okay, yeah. But see, I'll suggest you something like take few things for granted. Like just believe that okay, मोदी जी ने बोला है तो कुछ सोच समझ कर तभी बोला होगा. Then move
Okay.
forward. Like if you get stuck at everything and try to dig back to first principles, then it will be difficult to learn more. Everything you learn well, but your total volume of learning will be less.
That's what my life problem is actually. You come across. Thank you very much.
So
Actually, yeah,
take certain things on blind faith. Blind faith is also useful in many cases.
yeah. But it is like something like because the same thing. Actually, I got the suggestion. So that was the next part I have completed.
Hmm.
But still, the same things are going in mind that how this wave is going. But thank you very much. Like it is
Okay,
really
okay, no problem.
okay.
No problem.
Can I leave or should I stay?
Stay
Whatever
back.
you.
Come on, there are seven
Okay,
questions
okay,
remaining.
okay, sure.
So you have to arrange the steps of von Neumann stability analysis in the correct order. So I have four steps over here. They are sort of jumbled up. You have to arrange them in order, the same order in which von Neumann stability analysis is performed. So the steps are as follows. Step 1 is check whether amplification factor is less than 1. Step 2 is determine amplification factor or growth rate, same thing. You have to, step 3 is expand the error in its Fourier series. And step 4 is write the error expression from the finite difference equation. So we have a response in favor of option B, that is 4321. Let's take a look at the solution. It is indeed 4321. Good. So basically we start at the last one and go up. So the first thing definitely is write the error equation in its finite difference form, then expand the error in its Fourier series. Then each component of Fourier series will have the same growth rate. You have to determine that. And once you have done that, you just have to check whether it's less than 1 or greater than 1. So that tells you whether it's stable or unstable. Good. Now, next question. Question 5 is asking us what is the stability criterion for beta scheme for parabolic equation? So, parabolic equation, I'll write some. This is an example of a parabolic equation. Now, you have to, if you discretize this using the beta scheme, what and given that beta is between 0 and half, what would be the stability criterion for it? And there are four options here, and given gamma x is nothing but capital gamma into delta t divided by delta x squared. So is it option A, gamma x less than 1 over 2 into 1 minus 2 beta? Is it option B, gamma x has to be less than 1 over 1 minus 2 beta? Is it option C, gamma x less than 1 over 2 1 minus beta? Or gamma x over 1 plus 1 over 2 into 1 plus 2 beta? Not covered now. Okay. So let's just go to the solution. It's 1 over 2 into 1 minus 2 beta. So basically, if you go back to the lectures, this was, uh, this exact derivation was shown. So basically, it comes down to this. So gamma x into 2 into 1 minus 2 beta into some sine square of the wavelength. This thing has to be less than 1. Now, sine square, the sine square lies between 0 and 1. So you consider the worst case possible here, that is sine square being 1, the greatest value. Then you're left with gamma into whatever is less than 1. So then you take everything else to the right hand side, you get 2 into 1 minus 2 beta. Alright, moving on to question number 6. What is the expression for artificial viscosity in the first order upwind scheme for first order wave equation where lambda is the Courant number? Where lambda is the Courant number. So C into delta T over delta x. So what is the expression for artificial viscosity? Is it option A, alpha equal to c delta x over 2 into lambda? Is it option B, c delta x over 2 into lambda into 1 minus lambda? Option C, alpha equal to c delta x over 2 into 1 plus lambda? Or is it option D, alpha equal to c delta x over 2 into 1 minus lambda? So you get this from the modified equation, basically dou phi dou t equals minus c dou phi dou x plus there is something. So there's actually alpha into dou 2 phi dou x square which appears. So what is the expression for this alpha? Take a guess. Option B. Okay. So let's take a look at the solution. It's actually option D, close enough. So this comes from the derivation. So this is what appears as the artificial viscosity. And as it turns out that for lambda exactly equal to 1, this viscosity vanishes and this artificial viscosity vanishes and you don't get the uh, errors associated with it. Moving on to question number 7. Okay, this you will be able to answer. Where does artificial viscosity originate from? Is it round off error, truncation error, or discretization error? C, discretization error. Let's take a look at the solution. It is discretization error. Good. So basically, due to the scheme of discretization which we have done, we introduced these spurious derivatives which were not part of the original equation. And that sort of creates this artificial viscosity, as well as if it's a third order or any odd order term, then it introduces some other effects. But yeah, the source of that error is the error in the discretization. All right, so let's move on. What are the effects of artificial viscosity on the solution? So this is the nature of the error that it brings in. Is it option A, numerical dispersion? Is it option B, numerical dissipation? Is it option C, both A and B? Or is it option D, none of the above? Numerical dissipation. Let's take a look at the solution. It is numerical dissipation. Good. So dispersion and dissipation, they are both sometimes together called numerical diffusion, but there are certain exact things which they mean. So dissipation basically means the solution getting smeared away. So if this dotted line was the real solution, what we get is something like this. So it's sort of smeared away. We lost the sharp um, profile of the solution. And what dispersion does is that it introduces some wiggles. So basically, we still have the sharpness, but we get things like this near the uh, sharp changes. All right, coming to question number 9. So 9 and 10 should be very simple. So you have to match the following in relation to numerical effects in the modified equations. So what do even terms and odd terms result in? Is it numerical dissipation or numerical dispersion? So there are two options, A1, B2 or A2, B1. Option A, A1, B2. Good. So that's the correct solution. So even terms, the terms like dou 2 phi dou x square, and then dou 4 phi dou x power 4. These are even terms and they lead to dissipation type of error. and odd terms lead to dispersion. So odd terms like the third derivative of phi, fifth derivative of phi, and so on. And the last question is regarding the actual numerical effects. Is it smearing or wiggles? What corresponds to dissipation and dispersion? Once again, only two options, A1B2 and A2B1. A. Once again, A1B2. So smearing is a result of dissipation and wiggles are the results of dispersion. Correct. All right. So those are all questions from my end. Thank you for joining. We'll meet again next week.
Just 2 minutes,
Yeah,
just a few seconds.
sure.
Uh, Seriously, like I don't have words, but thank you very much because if you have
Thanks.
not explained to this limit, it's very difficult to move forward like this, the Fourier series and everything you have taken this much time to make me understand. Thank you very much.
Okay.